Welcome. We are coming up with another video to explain the velocity profile of plate flow or a slit. Now, what is the definition of slit? Actually, this kind of flow we encounter in case of plate heat exchangers. So what happens is that gap between two plates is quite small. Wherever this particular width is quite large, okay, and fluid is flowing through this gap from left to right. So this is one plate and this is another plate. One plate is being placed above another with some spacing provision for maintaining the spacing or some spacer, and in case of plate heat exchanger you know that gaskets are used. Okay, so with some support that gap is maintained, then fluid is made to flow from left to right because of pressure. Okay, then what happens is that the gap is quite small as compared to, or you can in this particular case we can say that in z direction distance between the two plates is quite small as compared to the width of the plate, which is actually we are saying that W means quite large width in y direction, and flow is happening however in x direction. Okay, so now for this analysis what we are saying that, okay, let us consider not the whole layer of fluid but a very small layer of the fluid whose thickness is actually delta z, but width is remaining W again and it is moving in x direction. Therefore actually while considering this particular strip, you will have to recognize that this flow pattern will be symmetric with respect to the central plane. At this center the velocity will be maximum, towards the top and towards the bottom that velocity is decreasing, and at the interface with the top plate and bottom plate the velocity is becoming 0. So the midpoint is of concern actually. See this, there is a axis passing through the midpoint and this central plane. So fluid moving at the central plane will be moving at the maximum speed. So now starting from the central plane above, whatever we are showing on the right hand side, that starting from the central plane whatever is fluid layer is there above it. So for that layer let us consider a layer of thickness delta z, so that bottom side's coordinate z coordinate is z and top side's z coordinate is z plus delta z, and width remaining same W. Okay, now for that layer of fluid let us consider thickness of delta x from the left hand side some position. So this is the position x, so therefore this position here will be x plus delta x, and this height is delta z. Okay, and you see we are showing that it starts from z is equal to 0. So whatever is happening at the top, similar means incident we will be seeing at the bottom side also, and that will be symmetric to it. So we are not considering in our discussion. So whatever happens above 0 will be just replicating it in the same way for the fluids falling below the central line. Okay, so now one element is considered at location z with dimension of delta x, delta z and W. Now you see actually this video we can see in context of the earlier videos as well, where actually one for the horizontal pipe flow and another one is actually this W. In case of even falling film we have been having that width of W. Okay, however in case of falling film the flow was happening due to gravity, and in this case it is pressure flow just like your while deriving Hagen-Poiseuille's equation. Okay, so now net positive forces acting in positive x direction here will be near to the maximum velocity. So here maximum velocity occurs at location z is equal to 0. So positive z direction here will be the higher positive, you can call it positive shear stress will be acting in this direction, and at location z plus delta z it will be acting in the opposite direction, because you see we are expecting that velocity profile will be like this. Means near the center it will be higher, and near the top surface it will be 0. Okay, therefore actually see what will be saying, the positive directional forces, that this particular value minus this one, this is in negative direction, multiplied by the this height del, sorry, it is for this one only, sorry, shear stress only, so this length multiplied by the width across this plane, so that is W, delta x into W. Now what is acting, what is causing the fluid to flow is actually pressure. From the left hand side there is Px, and from the right hand side P at position x plus delta x. So now Px is supposed to be greater, then only actually the fluid will be moving from left to right. So at Px, we are talking about this is a positive forces, so Px minus Px plus delta x, the whole thing should be multiplied by this particular, you see, this particular distance, that is delta z into W. So this pressure force is acting on this particular height and depth of W across this plane. Okay, so now both the sides you divide by a factor called delta x into delta z into W, then you are going to get this particular expression. So tau zx x minus tau z del x, del p del x. Okay, now this is the, you see, what you call is the hydraulic gradient or pressure gradient causing the fluid to flow. So this same thing actually we sum it up as a delta p by L. L is the, you see, length of the passage through which the fluid is flowing, and left hand side's pressure is quite high, maybe see you are maintaining hydraulic head by some overhead tank or by use of some pump. Okay, so delta p by L. So however, numerical value of delta p by L, you will be seeing that actually geometrically or mathematically it will be negative value. Okay, so now this expression, so we are just simplifying it for, because they are constant terms, delta p by L, we are writing as a delta p by L. So now we can integrate by separating the variables. Then we get tau zx is equal to delta p by L into z plus a. Again, you see, this is constant of integration. So now boundary condition is applied. Tau zx is equal to 0 at z is equal to 0. Means there is no shear stress. So no shear stress means actually, see, what we will be seeing that tau zx actually involves one term, change of velocity with respect to position. So now if we are getting maximum value here, it means, you see, the derivative here with respect to position will be 0. So therefore del tau zx is 0 at when, at the midpoint when z is equal to 0. So this leads to a is equal to 0. It means tau zx is equal to delta p by L multiplied by z. Okay, z means position, its position starts, you will have to measure that position with respect to the midpoint of this particular gap. Okay, so there is a central plane, from the central plane we will be moving upward, that is the position z. So now this part is quite similar to the whatever we have done for falling film. You see, now for Newtonian fluid, tau z is equal to delta p by L into z, means minus mu into del Vx del z is equal to delta p by L into z. Remember, x is equal to minus del p mu L into z square by 2 plus b. It is another constant of integration. So now for the boundary condition, that at z is equal to half thickness, now is half of the gap between two plates is, basically we are saying it is 2 times of delta. Okay, so now at half thickness, now you see your 0 starts here at midpoint, so upward also it is, you see, delta, and down also it is delta. Okay, so therefore at positive delta upward here, this velocity is 0. So then what we get, Vx is equal to delta p by 2 mu L into delta square minus z square. So this same similar expression as we have obtained for falling film, only thing is x, here it is z, in earlier case it was x, and here this velocity is Vx, in earlier case it was Vz. Okay, so then you see what is the maximum value? Maximum value is this particular term which gets multiplied with the factor 1 minus z by delta square. So this is maximum velocity. So this expression for v in x direction at position of z is equal to this one. This one is the one of the expression. So this expression we are writing again in terms of Vmax. So it is Vx is equal to Vmax into 1 minus z by delta whole square. Okay, so half thickness. Then V average is again in the just like in the previous case we can do, and this integration is just similar to whatever we have done for falling film, and then it is what we get is 2/3 of the V maximum. So it is similar to the falling film. So now this is all right. Now one interesting thing happens. What about the Reynolds number? Okay, here is the condition for slit flow. We have used the term called slit flow. Slit means actually small opening between two walls. So then you see width of the wall is quite great. W is quite great as compared to the gap between two plates. So that is the real slits. Okay. Then the by definition of hydraulic radius is what is the definition of hydraulic radius? This is flow area divided by weighted perimeter. In this case, flow area is W into thickness. So this is just like an opening. You see, this is W and this is the flow. Therefore, the flow area is W into twice delta. Okay. So then what is weighted perimeter? 2 times of this approximately equal to W. So therefore denominator is 2W and numerator is W into 2 delta. Okay. So then it comes out that means hydraulic radius is equal to delta, means half thickness. Then hydraulic diameter, you will have to remember this particular factor. Hydraulic diameter is 4 times of the hydraulic radius. So it is 4 delta. Then therefore we get that Reynolds number is equal to rho v dh by mu. So now you see dh is 4 times of that half thickness. 4 times of half thickness into rho into v average by mu. Now friction factor, you can recollect whatever we have done for this horizontal pipe flow. Friction factor is equal to wall shear divided by kinetic energy term. Now wall shear divided by V average divided by half of rho into V average. Okay, so then we can get expression based on whatever we have already derived. Okay, so V average expression in terms of means V maximum you can see there. All right, and then this term, okay, that is for the wall shear delta P. This we can get from this one. You see, wall shear is when Z is equal to half thickness. So then delta P by L into the half thickness. Okay, so then denominator is half into rho AVG. So this leads to 6 mu by delta rho V average, 6 mu by rho V average into delta 24 by rho average 4 times of delta by mu, which leads to 24 by NRE. So then you can estimate the friction factor for this particular slit flow as well. Okay, that is equal to 24 divided by Reynolds number. And after obtaining this friction factor, you can use that particular relationship. What was that? 4FL by D half rho V square. So now here is that D will be, or you can call it, you see, instead of DH you should write 4 times of this half thickness, and you can write here 4 FL by hydraulic diameter into half of this kinetic energy term. So this way you can calculate the pressure drop during the flow of Newtonian fluid in a slit. Thank you.